Hello everyone, this is Sai Divya Uka. This video is a part of assignment for the course COT 5405 for fall 2021 and my instructor name is Dr. Sharma. In this video, I'm gonna explain about a lower boundary for the problem called element distinctness. So the whole video will be in three parts. In the first part, we will see the problem statement. And the next, we see why we can't use sorting lower bound for this problem. And finally, we'll come up with a new approach to prove the lower bound for the element distinctness problem. So first, let us see the problem statement. The problem statement is the element distinctness problem asks if all the elements are different, my answer should be yes, or else it should give an answer as no. So let's consider if we pass this array into our algorithm, the answer should be yes because the elements in the array are distinct. If I send the B array into my algorithm, my answer should be no because the element is repeating. So this is our problem statement. To solve this problem, so one approach is, so let's consider we have taken an array consists of 4 elements. So the first approach is comparing every element with the each other element. So if we did this problem in this process, the time complexity will be, so the time complexity will be around big O of n square. So which is not a effective solution. So another approach to solve this problem is, first we gonna sort all the elements. So and then we will compare the adjacent elements. So for sorting, it takes around n log n times. And for adjacent comparison, it will take n minus 1 comparisons. So overall, the time complexity for this method will be, okay. So finally, the time complexity for this method will be big O of n log n. So our question is, can we improve this? Like, can we do better than this time complexity? So unfortunately, the answer is no. So in this video, we gonna explain like how to prove the lower boundary for this problem. Okay, let's see how to solve this. Oh, sorry. So here the two is repeating, not 6. So the answer is no. So first we will try to prove by using sorting lower bound. For that, we need to understand the decision tree because sorting lower bound will be proved by using the decision tree. So this is a small example for the decision tree. So for as an input, we will take as a set of numbers, and the program we used for the decision tree is called a labeled program because each node is associated with the ing. ing is nothing but integers, and the leaf nodes are considered as a output, and each edge will be associated with the comparison operators such as less than, greater than, equal to, etc. In the decision tree, the execution will be like this. It starts from the root element and it slowly reaches to the leaf node by satisfying the each condition. So if it's for example, we take this as a root node, and if satisfies this condition, then only it goes to the next node. So this is it's a quick overview about the decision tree. For better understanding, let's consider an example. So this is a decision tree for sorting 3 elements. We consider 3 element as a 9, 3, 9, 3, 8. Each here, if you see, each node is labeled with the integers. These are nothing but indexes of the array. If we pass this array into the decision tree, the execution will start from the root element, and based on the condition, it will reach the leaf node. So if we consider this element, it goes like this way, and it finally reaches to the this leaf. If you see this tree, we came to know that if our number of integers is 3, and the possible leaf nodes will be the 3 factorial, that is nothing but 6. If you see in the diagram, we have 6 leaf nodes. So from this, we understand that for sorting lower bound, if our array consists of n elements, the possible outcomes will be at least n factorial leaves. So each leaf is a permutation of a input. And the time complexity for this process is it is the tree height, because at least in the worst, if we consider the worst case also, it will take to reach the last node, which nothing but the height of the tree. So from the sorting lower bound, we know that the height of the tree will be like log of n factorial, so which is equal to the omega of n log n. If we try to implement this method to our problem, so in our problem we have only two solutions. One is S if the all elements are different. Another one is no if elements are repeated. So if we apply this in log n factorial, that is log 2 factorial will become 1. So this is explaining us we are using only one operation to decide whether the output is S or no. That means we are using only one operation to say that all elements are distinct or not, which is not possible. Like, so this is the main reason we cannot use sorting lower bound for our problem. Finally, we came to know that we cannot use sorting lower boundary for this problem. So let us see the new approach. So in our new approach, our main goal is to prove that T of n is a omega of n log n. So before proving the this main claim, we need to consider that there is a x point which consists of a x1 to xn coordinates in a n-dimensional space. And we will apply the restriction that this point should be in between 0 to 1 for our better understanding. And then we gonna consider another three claims to which leads us to prove the main claim. So before going to the claim one, let's understand why we are using the n-dimensional space. So for us, it will be very hard to imagine n-dimensional space. So for our convenience, we have taken the 2D dimension. So here we have taken example x point, which consists of a two coordinates. If I take my x array is like 0 0.5 comma 0 0.7, the point will be somewhere around here. If I take like example as a 0 0.7 and 0 0.5, the point will be somewhere around here. So if I take my third example as a 0 0.50 and 0 0.5, my point will be around here. From this, we can conclude that if my coordinates lie in the upper and lower triangle, so we can say that the elements are distinctness. That is, our output is S. If we take the coordinates as the same, it will lies on the diagonal. So the point which lies on the diagonal, then the output will be no. So from using this dimensional space, we can say that whether the taken array is distinct or not. Let's start with the claim one. So our claim one is to prove that R of L is connected. So R of L is considered as a region of leaf nodes, that is instances which reach the leaf node on a execution. So before proving the claim one, first we'll understand what is connected. So let's consider a region R where X and Y instances belong to the R region. If there is a path between X and Y, passing through the entirely R, then this region is said to be a connected R region. If there is a path which is a straight line, then we said that this region as a convex region. So example for the convex region we considered as a cube. So for easy purpose, in this theorem, we gonna prove that R of L is a convex, which because convexity is a special case of connectivity. Now let us see how the pictorial representation of R of L is connected. So for our example, we have taken a point X, which consists of three coordinates. So consider this is X1, this is X2, and this is X3. So we know that in a decision tree, the execution starts from the root, and by satisfying the each condition, it reaches L node. So if we take this condition as X, X3 less than X1, this point will be located in the phase, the corner which is facing us. So the point will be located in this region. If we chop that particular region, then the region will be in a convex manner. If we consider another condition like X3 is equals to X1, so the point will be located in the, sorry. So the point will be located in this region. So if we chop that region also, the chopped region will be in a convex manner. So in conclusion, we are saying that each node is associated with some condition. So if we slice that particular region of condition, then the remaining part will be also in a convex manner. So here the slicing operation maintains that convex nature. If we repeat this in a several times, then the last piece also will remains as a convex. So by this pictorially we can say that R of L is connected. So now let's see R of L is connected in a more formal way by doing this proof. So for this proof, we are considering X instance, which consists of a x1 to xn coordinates, and y instance consists of y1 to yn coordinates. So in this proof, totally there will be 3 executions will happen. In first execution, the X instance will reach to the L node in a specific path. So in a second execution, node Y also will reach to the same leaf node by following the same path. In third execution, we are taking a Z instance, which consists of a Z1 to Zn coordinates, and the coordinates will be based on this equation. So this equation is a straight line equation. Here we are taking a condition that lambda should be in between 0 to 1, because if we take lambda as a 0, then the x part will become 0. If we take lambda as a 1, then y part will become 0. So for that, to take the half of the x and half of the y, we are taking lambda in between 0 and 1. This means consider this is a x instance, this is y instance, and the z is lies in between the x and y instances. So okay, now consider the root is the root label is ij, and the first condition is considered as a less than equation. Like what I'm saying is, this is a root. To go to the leaf node, the first condition to satisfy is less than. So on first execution, xi will be less than xj. So xi coordinates, x coordinates will satisfy the condition. So y coordinates also follow the same path because both are reaching to the same L node. If I multiply lambda on both sides to the x coordinates, and if I multiply 1 minus lambda on the on both sides of the y coordinates, then I will get this equation, which is nothing but zi is less than zj. Here we are saying that the path which followed by the x and y instances, so automatically the z also following the same path. From this, we can say that this is X and this is Y. By following some path, the answer of S is, leaf node. And the answer of Y node will be reaches to the S node. Then automatically Z also will reach us to the S node. We have seen just now by seeing the proofs. So here we came to know that so in conclusion, what I mean is the path which is following by the X and Y. So the Z instance is also following the same path. From here, we can say that R of L is convex because the path is straight line. So convex is nothing but R of L is connected. So from this proof, we say that R of L is convex. Now our next job is to prove the claim to. So let's see what is claim to. So the claim to is, here we are taking two instance X and Y, which consists like n coordinates. But here the special condition is Y is the permutation of X. So our main task is to prove that X and Y will reach different S leaves by different paths. This is our main task to prove. So let's see how to prove it. So our job is to prove this. So X reach to L node in a different path and Y reach to another leaf node in another path. So these can be proved that, let's assume this is X instance and Y instance. If we prove that the answer of X is S, that is it reaches to L1 node, and the answer of Y is S, that is L2 node. If we prove that the Z point as a no, then our job is done. It means we proved that they both are not following the same path. So let's see in a more formal way. Okay. So in this proof, we are considering X and Y. Y is a permutation of X. So this we are proving this proof by the proof of contradiction. So for that, we are assuming that both instances are reaching to the same leaf node. So for that, we are considering that the answer of X is also leaf node. The answer of Y is also same leaf node, which following by the X. So let us assume that there is a path, there is a connected path between X and Y points. And we are assuming that another point Z, which is lies in between X and Y. So to prove this claim, we are considering another subclaim as that we are taking another subclaim as Xi is less than Xj and Yi is greater than Yj. So let me explain why we are taking in that manner. So for that, I'm taking an array which contains 3 elements, and I'm considering Y, which is a permutation of X, as a 963. If we consider condition as Xi less than Xj, so this condition works for the X coordinates. Like this condition is works for these 2 elements and these 2 elements. If we apply the same condition for the Y coordinates, so the condition will be goes wrong, because the Y elements are different from the X elements, because it is a permutation of X values. So this is the reason why we are taking as Yi is greater than Yj. So now we understand that why we are taking that subclaim. So let's get back to our proof. So now we have understand the subclaim. Now for proof's sake, consider a function f of w is equals to wi minus wj. If we apply this function to the X and Y instance, then f of X will become less than 0, because our Xi is less than Xg. And f of Y will become greater than 0, because our Yi is greater than Yj. So by mean value theorem, value theorem, we'll get that f of z as a 0, which means zi is equal to zj. That means like two coordinates in a point are same. So hence our answer will be no. So our job is done. Here we have proved that z as a no. That means we have proved that x reaches to the one leaf node and y reaches to the another leaf node in a different paths. But still they both are connected, because consider this is a x instance and this is a y instance. So we are proved that, so this is a z point, we proved in a such a way that this leaf node is joined to the z and it is joined to in this manner. Till now we have proved the claim 1 and claim 2. Our final job is to prove the claim 3. So our claim 3 says that it requires, number of s leaves, it should have at least n factorial. So from the claim 2, we have proved that each instance, that is permutation of the input, will reach us to the distinct s leaf in a distinct path. So from the claim 2, we can say that the possible permutations is n factorial, which means there are n factorial s leaves. So as we know that if the possible answer has at least n factorial leaves, then the time complexity will be log n factorial. So which indeed is equal to the omega of n log n. So in this manner, we have proved the lower bound for the element distinct problem. In conclusion, in summary, from this new method, we have proved that the instances which reach the S leaves from a connected region in an instance space. And secondly, we have proved that no instance partition the instance space such that distinct permutations are not in a same connected region. And finally, we have proved that from a claim 1 and claim 2, number of S leaves will require at least n factorial leaves. So finally, we have proved the lower bound for the element distinctness problem. And thank you for watching this video.